So I thought I'd work an example problem for you, applying some of the knowledge that we've learned about Schrödinger's equation and the probabilities and the normalization condition, so that you could help do your homework. So to remind you, we talked about the one-dimensional time-independent Schrödinger equation, and in this introductory modern physics class, that's pretty much all we're really going to be doing is solutions of full solutions like this one. So the Schrödinger's equation, as it applies here for a mass m, moving along the x-axis only and interacting with its environment through a potential energy function which is only dependent upon the x-coordinate and not time. And that allows you to use the time-independent Schrödinger equation. And here remember that the potential energy function is symbolized with U, E is the energy of the particle, m is the mass, h bar is of course Planck's constant divided by 2 pi, and psi is our wave function. Now, this solution to this equation, the wave function solution to this equation, can be used to calculate the probabilities. And it must obey what's called the normalization condition. And this is a result of the fact that the particle has to be somewhere, okay? And if the particle is somewhere, then if you integrate the wave function squared, the absolute value of the wave function squared, over all space, over all possible solutions, then it's going to be somewhere with a probability of 1, okay, or 100%. And so that's the normalization condition. You find a solution to the Schrödinger equation, and then you force it to obey this normalization condition, usually by solving for some undetermined constants from the solution to the differential equation. Okay, so that's the normalization condition. The probability has to be 1 if you sum over all possible solutions. And also, you can use this wave function to find the probability. Remember, we have our probability density function, which is the absolute value of our wave function squared. And if you have a three-dimensional problem and you're trying to solve for the probability that it lies within a very, very small range of possible locations, then you can take that probability density function, absolute value of psi squared, and multiply it times your little dv or your little delta x, okay? So that's how you find your probability over a small range. If you want to know the probability the particle lies within a larger range, then you have to integrate that wave function squared, the absolute value of the wave function squared, over the range of interest with respect to the x-coordinate to get that probability. Okay? So that's what we're doing. So using these ideas, we're now going to work an example problem. Here's the example. I'll read it to you. A particle is described by the wave function psi of x is equal to b times a squared minus x squared for a range that x lies between minus a and plus a. And the wave function is 0 everywhere else. Now a and b are positive real constants. So first, part A, use the normalization condition to find the value for b in terms of a. And second, part B, what's the probability to find the particle at a over 2 in a small interval of width 0.01a? And then finally, what's the probability for the particle to be found between a over 2 and a? All right, so first, I wanted to go ahead and show you what this wave function looks like. So basically, b times a squared minus x squared for a and b positive and real is going to look like an inverted parabola offset from 0, as is pictured here. And the parabola is going to go to 0 at some point. Here I selected absolute value of a is equal to 2. So that's selected here. And then outside of that range, it's going to be, the wave function is going to be 0. Okay, so it will go on to 0 below minus a and above plus a. So that's our wave function. So moving on now, let's find the solutions. We're first going to do part A. We're going to solve for b in terms of a using the normalization condition. So remember, the normalization condition says that if you integrate the probability density function over all possible values, that has to be equal to 1. You're forcing that to equal to 1. Well, we have a piecewise continuous wave function here. So for x less than a, the wave function is 0. For x greater than a, the wave function is 0. And for between minus a and plus a, it was defined as was stated on the previous slide. So I have to then, in order to integrate over all space, sort of sum it up in this piecewise continuous way, the integrals. So from minus infinity to minus a, the wave function is 0. So the integral there is 0 dx. From minus a to plus a, I'm going to plug in for that wave function, which was b times a squared minus x squared. And then remember, I've got to integrate the wave function squared, so I've got that squared here, dx. And then, of course, for x greater than a, the wave function is 0 again, so I integrate 0 from a to infinity. Well, now, trivially, these two integrals for the wave function is 0 gives me an integral of 0 as well. So these are 0. And it's only this piece right here from minus a to plus a that I have to worry about and actually perform an integral for. So minus a to plus a, I'm going to expand that square, so I have b squared times a to the fourth minus 2a squared x squared plus x to the fourth dx. I've got to integrate that. And then force it to equal 1. So when I do that, I get b squared times a to the fourth x minus 2/3 a squared x cubed plus 1/5 x to the fifth. And then I must evaluate that from minus a to plus a. So plugging in those values, then I get 1 is equal to b squared times a to the fifth minus 2/3 a to the fifth plus 1/5 a to the fifth. And now plugging in for minus a to the fifth plus 2/3 a to the fifth minus 1/5 a to the fifth. If I simplify that expression, I get 1 is equal to b squared times 2a to the fifth minus 4/3 a to the fifth plus 2/5 a to the fifth. Simplifying it even further, that becomes 16/15 b squared a to the fifth. Now this is all forced to equal 1 here, and so now I can solve for b squared in terms of a, and I get b squared is equal to 15 over 16 a to the fifth. And that's our solution for part A. Now remember, I'm running through this kind of fast. Your mind might not work quite as fast with the algebra. So at any point, go ahead and pause the video and make sure that you can recreate my math so that you understand what happened here, okay? I'm going to move on to the part B solution. Remember, part B was to solve for the probability that the particle was located at x equals a over 2 within a very small range of 0.01a. So the probability that a particle is in the narrow range is the probability density function, absolute value of psi squared, times the width of the range of interest, delta x. So for this problem, our wave function squared is b times a squared minus x squared, absolute value squared, and then times delta x. We're going to plug in for the value of x of interest, which is x is equal to a over 2. And we're also going to plug in for the width of that range, 0.01a. Now, we've already solved for b in terms of a in the first part of the problem. So we're going to plug in for that, using b squared is equal to 15 over 16 a to the fifth. So when I do that, I get that the probability is equal to 15 over 16 a to the fifth, that's my b squared part, and then times a squared minus x squared squared, but plugging in x is equal to a over 2. So that's a squared minus a over 2 squared, and then I square that. And then times the width, delta x, which is 0.01a. So that gives me 15 over 16 a to the fifth times 3/4 a squared squared times 0.01a. Okay? Now, if I simplify for that, I end up with a to the squared squared times a, which is a to the fifth, divided by a to the fifth. So all my a's cancel. And then I'm just going to be multiplying 15/16 times 3/4 squared times 0.01. And when I do that, I end up with a probability of 0.005, that the particle is located within that narrow range, centered at x is equal to a over 2. So that's how to do part B. Now part C, I have to perform another integral, because it asks me for the probability that the particle lie between the values of a over 2 and a. And that's too wide a region just to use the psi squared delta x kind of way. So I have to do an integral. Luckily, I've already done this integral when I did my normalization condition, right? I'm just using different limits for the integration. So I'm integrating from a over 2 to a, b squared times a to the fourth minus 2 a squared x squared plus x to the fourth dx. When I do that, when I perform that integral, I get b squared times a to the fourth x minus 2/3 a squared x cubed plus 1/5 x to the fifth, evaluated from x is equal to a over 2 to x equals to a. When I perform that, first of all, I have to remember that I'm going to plug in for my value of b squared here, which was 15 over 16 a to the fifth, right? And then I'm going to evaluate at those limits. When I do that, and you can check my math here, make sure that you can follow along. It might take a few extra steps than I've listed here. When I do that, I get a to the fifth over 2 minus 2/3 a to the fifth times 7/8 plus 1/5, 31 over 32 a to the fifth. Okay? Now, yet again, the a's to the fifth cancel out. And then I'm just going to end up with 15/16 times 1/2 minus 2/3 times 7/8 plus 1/5 times 31/32. When I evaluate that, I get 0.104. So that's the probability that the particle lies in between a/2 and a. So there's a 10.4% chance, basically, that the particle is in between a/2 and a, given the wave function shown here. All right? Now that makes sense, because if you remember, if you look back at our wave function, the wave function peaked at x equal to 0. And so when you're at between a/2 and a, you're kind of here on the downward going part of this parabola, okay? Which isn't going to be as high a probability as somewhere else. Okay, I hope that made sense to you, and it should help you do your homework. And I'll see you in class.